Right, so we'll take a quick spin through velocity time graphs now and what you can and need to be able to do with them in GCSE maths. There's a strong possibility that you would have met these in higher tier science as well, in the physics units. So just like you have a distance time graph, which maps time against distance travelled, you can also plot a velocity time graph, which plots velocity, speed, against time travelled. And the way that this works, or what you can get off it, is how a particle or a body changes its velocity as time goes on. If the graph is moving in an upwards direction, that means its velocity is changing positively, which means it's accelerating. If you get to a point where the graph is flat, that means it's traveling at a constant velocity. If it's at a constant velocity, then it's not accelerating, so you could say its acceleration is 0. If its velocity is falling, then that means that it's decelerating. So what we can get off a velocity time graph is acceleration, which is the rate of change of its velocity. And what we have to do at GCSE level in order to ascertain its acceleration is we have to estimate its gradient. And the way you would estimate the gradient is if you wanted to know what the acceleration was at that particular point, you would draw a tangent to the curve at that point. So a tangent is only touching the line, is only touching the curve at that point. And then from there you would work out the gradient in the same way you would to find the equation of a straight line. So you'd work out the vertical distance and divide it by the horizontal distance. That's an uphill slope, so it's going to be a positive gradient, so it's a positive acceleration. If you were to do it over here, then that would be a negative acceleration. So the acceleration is the rate of change of velocity, and it's found by estimating the gradient of a tangent to the graph at a given time. So if the graph is flat, then velocity is constant. Acceleration is 0. It's not accelerating. Then the other thing that you can find from a velocity time graph is if you can calculate the area underneath the graph, then that gives you the distance the particle has travelled. So the area under the graph equals distance travelled. And again, at GCSE, that's going to be an estimate for most graphs unless it's drawn with straight lines. And the way that we estimate is using Trapezium Rule. What we do for that is we divide the graph into a series of strips which are going to be of equal width, but because we divided them into strips, the curved part estimates to trapezia, strips of trapeziums. So by calculating the area of each of those and adding them together, that enables us to come up with an estimate for the area. So you will need to know the formula for the area of trapezium. You're in the higher tier. It's given to you anyway in the front page, but that is something that you should be able to cope with. So the way that you're given the area of a trapezium on the paper is like this, where the area is a half A plus B times H. Our trapezia are standing on their edge and they look like this. This is your time axis, your horizontal axis, so that's flat. So we've only got one angled side, but that doesn't matter. These are our A's and B's, so we read these off the y-axis. And this distance is the time interval. And like I said, that's usually the same and it's often 1. So when we're working out our area of trapezium, it's that way around, but it's just the same thing. So it's basically the sum of the parallel sides times the distance between them halved. Okay, so that's what you need to know. Those are the basic facts of working with velocity time graphs and Trapezium rule. There's no reason that a question will link the Trapezium rule to that, other than it ties it all in quite neatly, but you could be asked just to find the area under any given curve using the Trapezium rule. Okay. Now, my apologies for the poor copying of these questions. This is one of the first ones that I did when I started Jones the Sums about 10 years ago. So it's a bit rough around the edges, to say the least. Maybe next year I'll produce a new one of these, but for now you want to see a video for the clip that's on there, so this is the one we'll work with. Right, let's get stuck in. He says looking for his pens. The graph of y equals 16 minus x squared is shown below for values of x between 0 and 3. Use the Trapezium rule with the 4 ordinates. Now what they mean by ordinates are, those are going to be the the parallel line parts. So that would be one ordinate, that would be another ordinate. So we've got x equals 0, x equals 1. So this is going to be my first trapezium. One and 2 will be my second, and 2 and 3 will be my third. So area of 1 will be a half, and then we're going up to there. So the scale for this is 2 squares is 1 unit, so that's going to be 16, plus this one, which will take us to 15, times the distance between them, which is 1. So that's going to be half of 31, which is, brain gone dead, 15.5. The area of 2 will be a half, and now it's this one, which is 15, plus this one, which is 10, 11, 12, times the distance between them. So that's going to be 27, half of 27 is 13 and a half. And then the third First one is 12, so you see there's an overlap from one to the other because it's a shared side, and then this is going to be 5, 6, 7, which is 19, which is 9.5. So the total area will be the sum of all of those, which is 15, 28, 29, 38.5. These could come up on a paper 1 or a paper 2, depending on how complicated the numbers are that you're working with. Question 2. The velocity, v meters per second, of a particle at time t seconds is given by the equation v equals t cubed plus 4t squared plus 1. Table of the values of t between 0 and 3 are given below, and the graph is drawn for you. Use a trapezium rule with 3 strips of equal width to find the approximate area of the shaded region. So equal width would be 1, 2, 3. To find the approximate area, so area of 1 will be a half, and then it's going from, you don't need to read it off the graph because they're giving the tables up here. When t is 0, v is 1. When t is 1, 6. So it's going to be half of 7, 3.5. Area of the second region is going to be a half. 6 is the first spike, and then when t is 2, it's 25. The distance between them is 1. So that's a half of 31, which is 15.5. And area of 3, half 25 plus this spike, which is 64, times 1, so that's a half of 89, which is 44.5. So the total area will be the sum of those, and that comes out to be 19 plus 44 is 63.5. The area found in part A represents one of the following. Area under a velocity time graph, as I mentioned at the start, is distance. Question 3. The graph shows the speed of a train in meters per second over a period of 100 seconds, starting at time t equals 0. Estimate the acceleration of the train at time t equals 40. So t equals 40 is there. So again, this isn't going to be brilliant because it's been reduced and it's lost a lot of its accuracy over printing. But what we want to do is draw a tangent at that point. So you want to try and get your slope so that it touches only at the point t equals 4. And what you want to try and do is to choose to extend your line to the point where it's going to be easy to read off values. So I've extended that line to there because I know it's 5 and 60, and to there because I know it's 2 and 10. So it makes working out the gradient easier than if I'd have taken it down a little bit more or stopped it further. So you choose the length of that line to suit yourself. So in order to work out the gradient, I need to know that distance there, which is going to be 1, 2, 3. And this distance here, mark it on, which is going to be 10, 20, 30, 40, 50. So the acceleration will be the gradient of that tangent, which is, and easy to make a mistake here, to find the gradient, it's the vertical distance, the difference in the y coordinates, over the distance in the x coordinates. So it's 3 over 50. 3 over 50, 0.06 meters per second squared. And hopefully from your science lessons you know that acceleration is that, or you could write it ms or m/s squared like that. That's equally acceptable. If you didn't write any units, you'd still get the marks. It's not specifically asking you for those. Now with that question, you know, a slight change in the angle of that tangent will make a difference to the acceleration. So from an examiner's point of view, there would be a range of acceptable answers for that question. B. The table below gives the speed of the train between time 70 and time 100. So time 70 and time 100. Use the Trapezium Rule with the values taken from the table to estimate the distance in meters between T70. So there's T70, and we're going up in 10. So there's my first trapezium. Here's my second, and there's my third, which is a triangle. So area of 1 would be a half. Time at speed at 70, 3.6 plus 2.9, and this time it isn't times 1 because it's going up in tens. So we got 3.6 plus 2.9 times 10 divided by 2 is 5. So that's 32.5. You could type it in exactly as you see it if you wish. I'll just show you how. So you would have half bracket 3.6 plus 2.9 close bracket times 10. Okay, so it's exactly as I've written it, and you get the same answer. So that's the area of 1. Area of 2. So now we're going from 80 spike to 90 spike. So 2.9 plus 1.8 times 10. So 2.9 plus 1.8 times 5, 23.5. And the area of 3 is a half, 1.8 plus 0 times 10. So that's going to be 1.8 times 5, which is 9. So the distance will be 9 plus 23.5 plus 32.5, 65 meters. And that's it. So that pretty much in those 3 questions cover most of the stuff you need to know about velocity time graphs and the trapezium rule.